Hi, my name is Mudinda and I'm here to help you understand maths better for free. Today, I'm going to help you understand trig graphs, and this is going to be on the basis of one important point. Always compare it to the original graph. The sine, cos, and tan graphs have a very specific structure that they follow. And any graph that deviates from that structure means the original has been adjusted just a little bit. So we need to understand what the original trig graphs look like and what kind of adjustments can be made to them. Let's get started with the sine graph. The sine graph starts here at the origin. Then it moves up all the way to a y value of 1 when x is 90 degrees. It then comes back to a y value of 0 when x is 180 degrees. Then it goes all the way down to a y value of -1 when x is 270, and it completes its cycle to come back to the y value of 0 at 360 degrees. So the original sine graph looks something like this. I'm going to call that the graph y is equal to sine x. That is the original sine graph. These are the exact points that it will always have. This is the exact shape it will always have. This is where it starts and ends always. The y is equal to sine x graph. But there are adjustments we can make to it. For example, we could call it or change it to y is equal to 2 sine x. Now what this does is it stretches this graph vertically. So it'll still start at 0, the origin, and it will get to its highest point at 90 degrees, but its highest point will now be 2. It will then go right back down to the origin at 180 as usual. But then it will go down to its lowest point, which is now at -2. Not -1, but still on that 270 degree x value. Then it'll complete itself at 360 once again. So this red graph, y is equal to 2 sine x, looks something like this. It's almost exactly the same as the black graph, it's just been stretched vertically. Another thing that you can do to the sine graph is you can shift it some units up. For example, I can shift this 1 unit up. The graph y equals to sine x is almost exactly the same as the black graph, except you shift it 1 unit up. So instead of starting at the origin, it'll now start here. Its highest point will be at 2, and at 180, it'll be back to its horizontal plane. Its lowest point will be at 0 and 270 degrees, and it'll still complete itself at 360 degrees. So this blue graph, y is equal to sine x plus 1, looks something like the following. It looks something like this. So it is almost exactly the same as the black graph. We've just shifted it 1 unit up. This is different to what we did with the red graph. The red graph was stretched on both upper and lower ends to be longer or taller, to start at -2 and end at 2. But the blue graph is still as long or tall as the black graph. The distance between its horizontal plane and its highest point is just 1. The distance between its horizontal plane and its lowest point, that's also just a distance of 1. Just like the distance in the black graph was just 1. So the blue graph has not been stretched, it's just been shifted 1 unit up. Now, we can also do all this shifting at the same time. We can stretch a graph and shift it at the same time. For example, here's a Cartesian plane with the highest point at 3, then there's a 2, there's a 1, -1, -2, -3. And let's say this was 90 degrees, 180 degrees, 270 degrees, and 360 degrees. I want to try and sketch this green graph called y is equal to 2 sine x minus 1. This means from the original black graph, we're going to stretch this graph vertically. So that means the distance between its horizontal and its highest point will now be 2, much like this red graph here. The distance between its horizontal plane and its highest point there would be 2. So we're going to do the same stretching on this graph, but we're also going to shift it 1 unit down. So it's now no longer going to start at the origin, it's going to start here at -1. And then it's going to go up. Its highest point will be at 90 degrees. And in terms of y value, it would have to be at 1. And that is because since the horizontal plane is now here, we want the distance between here to be 2 long. So from -1 to 0, that's 1 long. And from 0 to 1, that is 2 long. Okay, so highest point will actually be at 1. It'll come back to its horizontal plane here. And its lowest point would be at -3. It would move 1, 2. Okay, because we've stretched it vertically by 2. And it'll complete itself at its horizontal point at 360. So this graph will look something like this. So that is the graph y is equal to 2 sine x minus 1. So all these little tweaks and additions that we're doing, let's look at one more example actually. Here's a graph, determine the equation of it. So this graph seems to start, let's say here at 1. Its highest point is at 3. Now that means that the distance between its horizontal plane and its highest point, from 1 to 3, that's 2. Then from 1 to -1, that is 2, right? From 1 we go down to 0 and then to -1, so the distance there is 2. Okay, so we now know that it must start with a 2 sine x. But as you can see, this graph, instead of starting at the origin, starts here at 1, so it's been shifted 1 unit up. That's how we know the equation of that graph. Awesome. Now this leads us to the general form of the sine graph. Y is equal to a sine bx plus q. We've seen that a stretches the graph horizontally. We've also seen that q shifts the graph up or down. We're going to discuss b right now, but I want you to note this is not the final form of the sine graph. It's not the final general form. I haven't introduced horizontal shift yet, and we're going to look at that in a second. What does b do to the graph? B has a lot to do with what we call the period of the graph. The period of the graph is how long it takes the graph to complete one full cycle. How long it takes the graph to start over again. So what we saw in the original sine graph is the following. It looked something like this. It started here at 0, and at 360 it completed itself. Now this graph keeps going after 360. But what you will notice is that at 360 degrees, it starts all over again. Remember the graph started by going that way, right? Then it went that way, and then it came back. Then it starts again here to go up again. So it's repeating itself at 360. And so we say that the period of this graph is 360. So the period of the original sine graph is 360 degrees. Is the period of every sine graph 360 degrees? Well, no, because like we said, there are some adjustments that can be made to this graph, and the challenge ahead of us is to be able to identify what kind of adjustments have been made. So B, like I said, helps us to find the period of the graph. But how does it help us to find the period of the graph? Well, there is a formula that helps us to know what the period of a sine graph is. The period of any sine graph is always equal to 360 degrees divided by the value of b in that equation. That is how we find the period of a sine graph. Let's look at some examples here and note that because we have this with period here and b there, sometimes we'll give you the equation of the graph with the value of b, and you can find the period of that graph by replacing b with that value of b. But sometimes we can actually give you the period of the graph and ask you to determine the value of b. So just solve for b there. Great. In A here, we've asked f of x is equal to sine 2x. Now that means that the value of A there is 1. The value of q here is 0, right? And the value of b is 2. You will remember that the general form is a sine bx plus q. If we have a b of 2 and we're trying to determine the period of the graph, well, remember that the period is always equal to 360 degrees over b, which in our case would be 360 over 2. So the period of this graph would be 180 degrees because 360 divided by 2 is 180. This means that this graph looks exactly the same as a sine graph, but it completes itself at 180, not at 360. So its highest point here won't be at 90, it will be at 45. It won't cut the y-axis at 180, it will cut it at 90. And it won't get to its lowest point at 270. Instead, that would be at 135. So it's going in intervals of 45 instead of intervals of 90. Okay, so that's what that graph would look like. Here's another example in B, and this time we've been given the sketch of a graph, and we want to be able to determine the value of B. So let's say this was y is equal to sine bx. We don't know the value of B. But we can see that this graph starts repeating itself at 180 degrees. That means that the period of the graph is 180. Now, since we know that the period is always equal to 360 over b, we can replace period with 180. Since we know that the period is 180, we can see that the graph repeats itself at 180. So we now have 180 is equal to 360 over b. Now by cross multiplying here, remember I've got two fractions here separated by an equal sign, so I'd cross multiply. 180 times b would be 180b. 1 times 360 would be 360. In order to solve for b, I can divide both sides here by 180. This gives me that therefore b is equal to 2 because 360 over 180 is 2. Okay, so this is the kind of question they could ask you regarding the period of the graph. Here's one more. We have a funny looking graph and we're asked to determine the value of b. We're not told a lot about it except that y is equal to 2 sine bx. We can see that the amplitude is 2 because the distance between its horizontal plane and its highest point is 2. The distance between its horizontal plane and its lowest point is minus 2. So we can see that it's been stretched by 2. Okay, but now we need to determine the value of b. We should at least know the period of the graph if we want to determine b. Let's try to figure out the period. Usually, this point here, or the sine graph, and remember we're comparing it to the original sine graph, yes? This point here is usually at 180, right? The highest point is at 90, cuts at 180, lowest point 270, completes at 360. But for some reason this time, this is not at 180. Instead, it is at 45 degrees. Okay, that's very weird. That must mean that the highest point here is half of 45, which is 22, let me divide 45 by 2 on my calculator. That's 22,5, right? So here would be 22,5 plus another 22,5, that's 45. And 45 plus 22,5, that gives me 67,5. So here you would have 67,5 at the lowest point. Add another 22.5. And here it would have 90 degrees. Okay, here it would complete itself at 90 degrees. Also makes sense because at halfway it's at 45, so it completes itself at 90. As we can see, the period of this graph is 90 degrees. And the period is always equal to 360 over b. In place of period, I put 90, so 90 is equal to 360 over b. If I cross multiply here, 90 degrees times b is equal to 360. Solving for b by dividing by 90 degrees, I would get that b is equal to, now 360 divided by 90, that's 4. The value of b is 4. Great. Now, here we are given that this black graph here is y is equal to a sine bx, and we're asked to write down the values of a and b. As you can see, the distance between its horizontal point and its highest point is a half. Distance between its horizontal point and the lowest point is negative a half. Okay, we can see this hasn't been shifted up or down. And we can also see that it completes itself at 360. Now, the fact that the highest and lowest point is the distance of a half tells us that a is a half. It's been stretched a half times. In fact, it's been squashed. Okay, and the period is 360, and we know that the period is always equal to 360 over b. So period is 360, so we have 360 is equal to 360 over b. So 360 times b is equal to 360. And if you divide both sides by 360, you would get that b is just 1. Okay. And we can also see that b is 1 because the graph does complete itself at 360. So the original sine graph, the graph y is equal to sine x, has an a of 1, a b of 1, that's 1 times x, and a q of 0. Okay, awesome. We're now going to discuss horizontal shift. Now, with horizontal shift, just like last time, I'll show you how it works first, and then I'll show you the final general form. Imagine we had this original sine graph here in black. Y is equal to sine x. This graph completes itself here at 360. Its lowest point is here at 270. This is 180. Its highest point is at 90, and it begins here at the origin. Imagine we shifted this graph 30 degrees to the right, so that instead of starting here at the origin, it starts here at 30 degrees and 0. Okay. And its highest point, instead of being at 90, is now at 90 plus 30, which is 120. So somewhere at 120, it then has its highest point. Or maybe that's not really 120, maybe somewhere here is 120. Okay. And let's say it comes back to the x-axis at not 180, but 210. Its lowest point is not at 270, but at 300. It completes itself not at 360, but at 390, right there. So this graph looks something like the following. It looks like this. Almost exactly the same as the black graph, except it's been shifted 30 degrees to the right. How do we write that on the equation? You say x minus 30. Now, this should ring a bell from how functions work. Original algebraic functions. I've made a whole series on algebraic functions. I suggest you give it a watch. It might actually help you understand trig functions as well. So that is what happens when you shift a graph 30 degrees to the right. Alternatively, imagine we shifted this 30 degrees to the left. So instead of starting here at 0, it starts at negative 30. Instead of its highest point being at 90, it's at 90 minus 30, which is 60 degrees. So its highest point is somewhere there. Instead of it returning to the origin at 180, it now returns at 150, so somewhere there. Okay. Its lowest point is no longer at 270, but at 240, somewhere here. It no longer completes itself at 360, but at 360 minus 30, right, which is 330, so somewhere there. Graph looks almost exactly the same as the original sine graph. It's been shifted 30 degrees to the left. That is the graph of y is equal to sine x plus 30. And I know it is a bit weird to think, why is it that it says minus 30 when shifting to the right and positive 30 when it shifts to the left? Our brains sort of feel like to the right must be positive, but that is not how it works. Now, this brings me to, I don't remember why I drew this. This brings me to the final general form of a sine graph. Y is equal to a sine b of x minus p plus q. Let's remind ourselves what each of these do. A stretches the graph vertically. B affects the period. The period of any graph, any sine graph, is equal to 360 over b. P has to do with horizontal shift. Okay. And Q shifts the graph up or down vertically. Okay, so that is the the general form of a sine graph. And remember that A and Q are different in that A stretches the graph like both ways up and down, it stretches it, right? And so it affects the distance between its horizontal, well, I've been calling it horizontal plane, but I mean, it's halfway point, horizontal plane, right? It stretches it equally upwards and downwards. It stretches the graph. Q instead shifts it, right? It doesn't stretch it. It shifts it up or down. Again, then B has to do with the period and P has to do with horizontal shift. We're going to always compare any graph that we see to the original graph y is equal to sine x, which has an a of 1, right? And therefore, the distance between its horizontal plane and the highest point is just 1, right? It has a b of 1, and so the period is just 360, right? It has a p of 0. It's not shifted left or right. And that's why we don't see minus 30 here, right? We don't see minus 30. We just see x plus 0, right? It hasn't been shifted. And q is 0. There's a 0 q there, right? So it hasn't been shifted up or down. We're going to always compare any graph to this original sine graph, okay? And that'll tell us what A is, what B is, and what Q is and P is if it wasn't given to us. Or if it was given to us, we now know how to sketch it by how those values deviate from these ones, okay? Awesome. The cos graph is almost identical to the sine graph. But instead of starting here at the origin, it starts here at 1. Then it goes down to the x-axis here at 90. And its lowest point is at 180 and minus 1. Comes back to the x-axis at 270 and completes itself at 360. Remember, completes itself means starts to repeat the same process, right? It looks something like this. And maybe I drew that dot a bit too high. It looks something like this. And from this point onwards, it's just going to repeat that same process, okay? And so it's just going to repeat the same process there. This is what we call the graph y is equal to cos of x. Now remember, we can shift or stretch. Let's start with the stretching. We can stretch this graph. Let's say we stretch it and it's now y is equal to 2 cos x. Okay, y is equal to 2 cos x. That'll mean the highest point is no longer here at 1, but it's now here at 2. The lowest point is at minus 2. Everything else will still remain the same. It'll start here, and it'll cut the x-axis here at 90, okay? It's just that its lowest point will now be at minus 2, cut back at 270 again, but highest point now at 2. So it'll look something like this. That's the green graph, y is equal to 2 cos x plus 1. Alternatively, we could have y is equal to cos of x plus 1. That's just shifting the black graph 1 unit up. Instead of starting at 1, and it's now going to start at 2. Its lowest point, however, will not be all the way here at negative 2 because it's not been stretched, right? The distance between its horizontal plane and its highest point should still be 1. So it's actually going to come down and have its lowest point at 0. So it's gonna, at 90 degrees, cut here at 1, and its lowest point here at 0, comes back to 360, highest point here at 2. Okay, so it's gonna look something like this. This is almost exactly the same as the black graph. It's just that we've shifted the black graph 1 unit up. It's horizontal plane somewhere here. Okay, the distance between here and there is 1. The distance between here and there is 1 because it hasn't been stretched. Awesome, that is the cosine graph. And this means that if we have a graph like the following, y is equal to a cos bx plus q. Write down the values of a, b, and q. Well, has this graph, let's determine a, has this graph been stretched? Yes. The distance between here, the horizontal plane, and the highest is 2. Here, the horizontal plane, the lowest is minus 2. So we can tell it's been stretched both ways up and down. So a there has to be 2. How about the period of this graph? When does this graph complete itself? It starts here, goes all the way down, back, and completes itself here at 180. So the period is 180. Now, mind you, the period of a cosine is exactly the same as the period of the sine, is 360 over b. If the period is 180, we have 180 is equal to 360 over b. 180 times b is 360. And dividing both sides by 180 gives me that b is equal to 2. So b is 2. What about q? Has this graph been shifted up or down? No, it has not been shifted up or down. It's only been stretched. Okay. And so we know now that q is 0. Q is 0. Okay, so the graph is y is equal to 2 cos 2x plus 0. That is this the equation of this graph. Okay, so you can see the sine graph and the cos graph are almost... All right, now here's another one. Write down the values of a, b, and q. Okay, so on this graph here, it sort of has a little horizontal plane here. Okay, the distance from here to there is 1. The distance from here to there is 1. So this hasn't been stretched. A is just equal to 1. Okay, it's just 1. What about b? What's the period of the graph? The graph starts here, all the way down and back up here. It completes itself here at 360. Because it completes itself at 360 means the period is 360, meaning b is just 1. Okay. And what about q? Has this been shifted up or down? Yes. This has been shifted 1 unit up. Okay. So we can see that q is 1. So y is equal to cos x plus 1. That is the graph there. All right. Awesome. Now, the general form of the cos graph is y is equal to a cos b x minus p plus q. This is because we can also shift the cos graph horizontally. Okay. Now, that said, we're actually going to discuss why and how sine graph and cos graph are similar. What I've drawn here is actually a cos graph, not a sine graph. Why? Well, it starts here instead of starting at the origin. Remember, the sine graph starts at the origin and goes that way. Okay. The cos graph, however, starts all the way at its highest point, at 1. So we can see that this is a cos graph. This is the graph of y is equal to, I'm only saying this because I know, but let's add more information to confirm that. Okay. This is the graph of y is equal to cos x. What would happen if you shifted this graph 90 degrees to the right? Now remember that here we have 90 degrees. If we shifted this graph 90 degrees to the right, just 90 degrees to the right, what would happen is that now this is actually at negative 90. This is at 90. This point here would move to come here. And this graph would now look like the following. Highest point at 90, cuts at 180, lowest at 270, completes at 360. So that is a sine graph. That is a sine graph. So shifting a cos graph 90 degrees to the right actually ends up in a sine graph. Okay. And what would happen if we shifted... Yeah, so the sine of... and what would happen if we shifted this red graph 90 degrees to the... So that red graph, let me write its equation here. Y is equal to sine x. What if we shifted that red graph 90 degrees to the left? Okay, then it comes back to look like this. It now becomes the cos graph. Okay, so that said, the sine of x, and let's shift it 90 degrees to the left. So plus 90 is equal to the cos graph. Shifting a sine graph 90 degrees to the left gives us a cos graph. If this is looking a bit too weird or messy, look at it afresh. Here's a sine graph. Okay, here's a sine graph. Here's 90, here's 180, here's 270, here's 360. Imagine shifting this graph 90 degrees to the left. This point here would come here at negative 90. This highest point here would come here. Okay. This point that cuts the x-axis would now be down here at 90. Okay. So the graph would now look something something like the following. Cuts here, lowest point here, and back to 270, and completes itself here. So as you can see, this red thing is actually a cos graph. This is a cos graph. Shifting a sine graph 90 degrees to the left ends up in a cos graph. The sine of x plus 90, shifting a sine graph 90 degrees to the left, gives us a cos graph. We learned in reduction formula, and if you haven't watched, I have a brilliant, if I do say so myself, a brilliant video on reduction formula. It's going to teach you everything you need to know, grade 11s and 12s, on reduction formula. But the sine of 90 degrees plus x, which is the same as the sine of x plus 90, is equal to cos of x. We also learned this fact in cofunctions in reduction formula. Okay, but keep that in mind, that shifting a sine graph 90 degrees to the left gives us a cos graph. Shifting a cos graph 90 degrees to the right gives us a sine graph. Lastly, we just discussed this, the sine cos relationship. Let's talk about the tan graph. Now, I don't have too much to say here. We'll actually see the tan graph in an example in our past paper example, which is going to be the video I post next. The tan graph has asymptotes, or lines that it never touches, at 90 and 270. And it starts this way, then repeats itself that way. So at 180, it's repeating itself. It just so also happens to have another flap there. Okay, this means that the period is 180, or the period of a tan graph is 180 over b instead of 360 over b. Okay, y is always equal to a tan of b into x minus p plus q. Almost the same thing as all the other graphs. Okay, if you change a to 2, so if instead of having this y is equal to tan x, you changed it to y is equal to 2 tan x, you would just make this closer to being a vertical line. So it would be steeper, something like that. Okay, it's becoming steeper and steeper. If you say y is equal to 3 tan x, even steeper, almost directly vertical. Oh, sorry, I shouldn't have that there. Almost directly vertical. Okay, like that. All right. So that's the tan graph, and we'll discuss more about the tan graph when we look at a past paper example. I hope this video has been helpful in helping you understand how to compare a graph, a trig graph that you're given, to the original trig graph, because that is going to be the only challenge. If you know how the original form looks, compare whatever you're given to the original form and you'll be okay. Let's do a past paper example together in the next.